So to begin with, I'm going to tell you a little bit about the equipment that we use in this course. So to start with, this is our motion sensor, and it works basically the same way that a bat's sonar works, in the sense that you point it at some object, and the sensor will emit sound waves, a little clicking noise that you can hear. The sound waves will bounce off the object, reflect back towards the sensor. The sensor can detect those, and then figure out how far away the object is. So what's neat about this is that you can do this repeatedly in real time. That means that you can actually create a real-time graph on your screen of position versus time. The object can be moving back and forth in front of the sensor, and you'll actually be able to see your graph moving up and down at the same time on screen. So if we can make a position time graph on screen, we can also make a velocity time graph or study the acceleration of the object. So this sensor is really good for studying kinematics. What we're going to be doing later in this experiment is we'll be clipping it to the end of a track, moving a cart back and forth, and measuring the motion of the cart on the screen. I'm going to show you the program that you're using today in a little while. That's not what you're doing at the very beginning of the experiment, however. To begin with, you're going to point this at a partner and have your partner walk back and forth in front of the detector. So your partner will be moving around in the room, and you'll be able to graph their motion on screen at the same time. Now there's a few things that you need to be aware of with this sensor. The first is that it has what we call a dead zone. So that's about 15 centimeters. Within 15 centimeters, the detector can't figure out how far away things are. And I'll show you that on the screen. Your graph will actually go flatline if the object is within 15 centimeters of the sensor. So for all of your experiments, you need to make sure that the object's at least 15 centimeters away, and then the sensor is good for up to a couple of meters. Another thing to be wary of is that the sensor can be confused by objects that are close to the object it's trying to study. So when you're pointing this at your partner, for example, make sure your partner is walking down one of the clear aisles between the desks. Otherwise, if the sensor detects some reflections off, say, a desk or the back of a chair, then you could get a really weird looking graph, just because it won't be following your partner. It'll be getting other reflections from other objects. Likewise, when you're studying something on the track, make sure that you don't have anybody's elbow or book bag sitting close to the track. Just make sure there's a roughly clear area in the immediate vicinity of the object that you're studying. Finally, there are two settings on this. So at the top of the sensor, we've got a little switch. There's a wide beam setting and a narrow beam setting. The narrow beam setting is for when you're studying a cart on the track, so something like this. But the wide beam setting is better for pointing at people. So to begin with in this experiment, put it on the wide setting and then point it at your partner. Now the detector considers the positive direction to be away from it. So if you're walking away from the detector, the sensor is going to consider that to be you moving in the positive direction. And now I am going to tell you about how to use the velocity program that we're using this week, and I'm going to show you that as a screen capture on screen. All of the programs that we're going to use this semester are housed in this 1100 folder. So look around on your desktop for the 1100 folder, double-click to open that up, and inside you should see a bunch of different programs loose, and also some folders for those experiments when we need to access more than one program. This week we're going to be using this velocity program down at the bottom. So you can double-click that to let it open up. Once it is open, what you'll see is a graph. This is where our data is going to appear on screen, and also a data table. So this is the data that is going to be graphed into the graph. Now up here in the corner there is this start button. When I click this, then the sensor is going to start making its little clicking noise and detecting how far away, in this case, the cart on the track is. So I'm going to demonstrate this for you. I've put the cart in the middle of the track, and I'm going to click start, and then I'm going to move the cart back and forth. And you will see on the graph how far away the cart is from the detector in real time. So I'll click start, and I'll move the cart towards the detector and away from the detector, and I'll stop, and you can see in real time what I was doing. So when I moved farther away from the detector, the position value became a larger number, and when I was closer to the detector, the position number was a smaller number. So again, you can see in real time how far away the cart was from the sensor. So now let me show you what it looks like when you move the cart right into the dead zone. So I click start, and then I move my cart towards the sensor, and I just keep going until I actually touch the sensor. But you'll notice that the graph actually goes flatline well before I get to 0. So this is the dead zone, and you can actually check that that's about 15 centimeters away from the detector. So anything less than 15 centimeters from the detector, it can't tell how far away it is, and it just gives you this flat line. So be careful to take all your data outside of 15 centimeters. So one thing you may need to do is resize your axes. So I'm going to show you how to do this, but it is a process that's kind of easy to forget. So I've also put a handout up on the website, and if you forget sometime in the future how to do this, you can just pop open a web browser and go and look it up. So it's on that handout. But anyway, let me show you how you do this. You go up to Display and then Settings. And by default, you'll be on the wrong tab. We actually want to be on this Axis Settings tabs. So you click that. And down here under Extras, you should unclick Lock Origin Position and Lock Scaling. So you deselect these and hit OK. What that allows you to do is that if you hover your mouse over top of one of the numbers, it'll change shape. You can't see that in this video, unfortunately, but it changes to a little squiggle with a double-headed arrow. So if I hover my mouse over top of one of the numbers, then I can click and drag to stretch and squish my graph. And I can do that on both axes. I can hover my mouse over one of these numbers and do the same thing. So if, for example, all your data is scrunched down at the bottom of the graph, then you would want to stretch it upwards by using this technique. You can also move the entire origin around. So for example, if I hover my mouse over the line, not the numbers, but the line, it again changes shape. And again, unfortunately, you can't see that in this video, but it turns into a little hand shape. So I hover over top of the line itself, and I can shift the whole graph around on the page. You probably won't need to do that in this first experiment, but it's useful to know that you can. So usually all you need to do is hover your mouse over top of a number and stretch things out so that they're easy to see. Finally, when you're all done using the program, you could just click the little X in the corner to shut it down. It will always ask you whether you want to save the changes. Just say no. Now, as I said, in this first part of the experiment, you're going to be pointing the sensor at a partner, and they'll be walking away or towards the sensor, as dictated by the lab manual, and you'll be capturing that motion on screen with the computer program, and then sketching what you see into your lab book here. So in this first question, what they have you do is they have your partner walk away from the detector at a constant velocity, and then they have them do it again, except at a slightly faster speed. So you want to draw both of those lines onto this graph, and then you're going to comment on the similarities and differences between those two lines. Now, when you're drawing this, go ahead and draw the little bumps and wiggles you see. So draw what you actually saw on screen. It doesn't have to be idealized in any way. Then they have you talk about similarities and differences, and specifically it's a good idea to talk about how you can tell which line is the one where the person was walking faster. In question 2, they're saying if you were to walk left, that is in the negative direction towards the detector, what would the graph look like? And they have you do something that is going to be very common throughout this whole semester, and that is they give you a space to make a prediction. And then later on you're going to do the experiment and actually draw what you really saw on screen. Your prediction should be the ideal world case, so what you expect to see theoretically. So ideal world means no bumps and wiggles, no friction, no wonky stuff because your partner couldn't exactly walk at a constant velocity. So you draw the perfect world case that you expect to see, and remember that constant velocity should be a straight line on a position time graph. And then you actually do the experiment and draw what you really did see, including bumps and wiggles and any weirdness of the data. And then they ask you to make a comparison between them. So when you make this comparison, you're comparing what you actually saw to what you predicted that you would see. And you want to talk about similarities and differences. So in what way was your real-world graph similar to the theoretical one? And in what ways did it differ? So the differences might be the bumps and wiggles, for example. It's never enough to say my graphs look the same. You have to be specific, and I recommend you use graphing language. So say things like they were both linear, or they were both curved, or they both had a y-intercept that was positive, or they both had a y-intercept that was 0. One thing that you don't need to talk about is whether or not the slopes were the same, because we don't have any numbers on here. So these are just sketches. We don't know what the slope values are. So if this slope looks way less steep than this one, that's actually not something that's physically relevant just because we don't know what the slopes are. So don't talk about slope, but do talk about things like the y-intercept, whether it's linear, whether the slope is positive or negative or 0. And then I won't say too much more about everything you do up to question 9 just because it's very straightforward. They'll describe some motion and they say make a prediction, so you draw the ideal world case and then you actually do it. You have your partner do what is specified in the question and you capture that graph and then you compare what you actually saw to what you predicted that you would see. So up to question 9, that's most of what you're doing. So in question 9, things get a little more sophisticated. You're going to be using the cart on the track, and so the first thing you do is you clip your sensor onto the end of the track and make sure that you are on the narrow beam setting. So you were on the wide beam setting when you were pointing this at your partner, now you want to be on the narrow beam setting. The window of your detector should be exactly vertical or maybe tilted slightly forward. That tends to give you the best data. Make sure that the area around the track is relatively clear of objects, just so that you're not confusing your sensor. Now there's something you always want to do every single time you use the track before you start taking data, and that is that you need to level the track carefully. So take off your cart and you get this spirit level. So a spirit level is just a clear plastic tube with a little bubble in it, and there's 2 lines on the plastic tube. When the bubble is in between those lines exactly, that means that the spirit level is sitting on a level surface. So you put this on your track parallel to the length of the track, and you check whether that bubble is right between the lines, exactly centered. And you want to be quite careful about that because there are certain experiments where you cannot get good data if your track is not level. So you check that it's level. If it's not, the way in which you fix that is way down here where you may have a little bit of trouble seeing it. This end of the track sits on a screw, and you can twist the screw to raise and lower this end of the track. So you do that until you've got a nice level track, and then you're ready to take some data. Now the motion that we want to study is going to be a slow exaggerated push and then a release. So slow exaggerated push and then you let go. And it's important that the push part of this be very slow and exaggerated because you're going to be capturing this on screen and it's hard to actually see it unless you do the push very slowly. So you would start the program running and then you put your finger on this, give a slow exaggerated push and then let it roll away. Now if you think about it, when your finger is actually on the cart accelerating it, what you should see on the screen should be an acceleration. In other words, a curved line on a position time graph. When you let go of it, when it's now just rolling, we expect that to be constant velocity, and on a position time graph, constant velocity looks like a straight line. So you need to make a prediction in your lab manual as to what you think this is going to look like. When you're accelerating it, you expect to see a curved line on your position time graph. When you release it, you expect it to then be a straight line. So you figure out how that should look. So one real-world effect that you might see is friction. So you'll be giving this a slow, exaggerated push, and then you let it roll away on its own. When it's rolling, you're expecting to see a straight line. You may not see a perfectly straight line. If there is friction, then what you would see on the screen is, instead of a perfectly straight line, a bit of curvature, and it would be curving downward because this thing is decelerating. So although that doesn't show up in your prediction, when you actually make your graph, you should say whether or not you saw any sort of effect like that. So if you saw curvature when you didn't expect to see any curvature, theoretically, then that may be a friction effect, and you would make a note of that. Now one thing that's unfortunate about this part of the experiment is that normally you'd make your graphs on screen and you just print them out and paste them into your book. This week and this week only, we don't allow you to do that. Instead, you're going to print out your data table and you're going to make a graph by hand. So you will graph specifically the roll part of this experiment, where it should look like a straight line. You'll fit a straight line through your data points and find the slope of that in order to get the velocity when it was just rolling freely. Like I said, normally you would just get to print out the graph, but this week alone we're going to make you do one by hand. So now I'm going to show you how you print your data. So first of all, this graph that I've got up on the screen is just a nonsense graph. It's got nothing to do with question 9, so this is not anything like what you'll see in question 9. However, in question 9, you're going to have a linear section like I've got here, and you want to highlight about 10 to 12 data points, and you're going to graph those by hand. So the way in which you do this is you click and you drag a rectangle that covers about 10 to 12 data points, and they will be highlighted on the graph, and they'll also be highlighted over here in this data table. Now most weeks you would just print this graph off. You'd click the graph to make sure that it's the active window and you'd go File, Print. This week and this week only we're going to make you graph this by hand, so instead you want to print the data table. So you click the data table to make sure that it's the active window, and you'd go File, Print, and you can increase the number of copies for the number of people in your group. Hit OK and it will print out somewhere in the room. Now, one thing you might want to look at is whether or not you have any friction effects. So during the roll part of the motion in question 9, theoretically we expect to see a perfectly straight line on this position time graph. If you have friction effects, the way in which they show up is that you would see a slight downward curvature. So rather than being perfectly linear, it would sort of roll over like so. It would curve. So look at your data and decide whether or not you have friction effects, and if so, then you maybe want to mention those when you're writing up the conclusion for your experiment.